Hi, today I will cover a problem longest increasing path in the matrix. Given an integer matrix, find the length of the longest increasing path. From each from each cell you can either move to 4 directions: left, right, up or down. You may not move diagonally or move outside of the boundary. Okay, and this is the example. We have this array. You can go only to the number which is bigger than this one. For example, from this node we can go here, or because it's 6, and or here. We cannot go here because it's the same. And we have to find the longest path that we can find here. For example, from here to this, and for example through this, and then this is 3, 1, 2, 3. And the longest increasing path is here 1, 2, 6, 9. This is the longest path, 4, and this is the answer. Okay, the first solution is, and the best solution here is the deep first search algorithm in the graph here, because we have here graph. We can treat it like a graph. These are nodes here, and we only want to find the longest path from one to another, and we have rules which how we can move. Yes, and that's all. So this is the answer here. There is nothing really matters. Okay, and also because if you want to check every single path, this will be n power of n, so the time complexity will be not so good. We have the here memorization, so we remember. For example, if you will be here once, we check the path. For example, we can go from here only here, and we remember this path, the count of the path, because this is a matter. So we remember and we save it in this memory. And in the next time when we go here, we can simply read this from the memory, not checking to the 9. Yes. So in this solution, we can go only through n complexity, because through all nodes we go only 1. Yes. And we use this. So first we go through this whole nodes here, through whole matrix, and for every point we run the deep first search algorithm, and we return the count. If the count is better than our previous one, then we save, and this is the return. Okay, and we go to the deep search deep first search here, and we go simply we check if the memory is in our memory, this node. If not, we calculate it. If is, we simply return it. If not, so we have to calculate it, and we check from the every position if the size, the value, we checking the value. For example, the next one, this if we are in this node, we checking this value 9, and this value 6, and this value 2, and this is one bigger. Then we go deep search, first search 1 again with this node, and with the next node, and we return to our max count. And on the end, we checking which was the max, and we remember in our memory this max, and we also return it. And this is how it works. Yes. This is one solution, the most simplest, we can say. This also here the we can say approach when we don't use something like that. We can make a other matrix when we can save the only direction. It's better because when you sometimes want to extend problem, and for example also the diagonally, there will be no problem. There will also another simply another node in the matrix. I can show you this in the other solution here. For example, here we have structure direction. In this direction are two things, and simply we have here vector direction dir this direction in this, and then simply we, for example here, for every direction here d, we simply add the 0 1, yeah. So this here 0 and 1, 0 and minus 1, minus 1, 0 1 and 0. Okay, and this approach generally is about the directed acyclic graph, and this is about we have here also the graph, and we have directed graph because from this we can go only here, we cannot go here, and we have to find the only the path here. So we can calculate it like this. This is only prepare the matrix, the tab, it is the same like matrix, only one bigger, but doesn't matter. Out degree, we calculated if for every point here, if the point of the next one is bigger, for example here, we putting it +1, starting from 0 everywhere. So here will be 1, here will be 0 because nothing is bigger than here. Here will be 1 and 1. Sorry, for this will be 2, 1 and 2. You calculate this help out degree matrix, and we going through this out degree and checking if sum is 0. If it's 0, that means that is the leaves. This is the end point. For example, here is an end point, here is an end point, and here is an end point, because from this point we cannot go any further. Yes, because this is the biggest in this area. Okay, and we have here main while, which we checking if these leaves are not empty. We have here a stack, probably list, and we checking if not empty. First we have this 1 2 3 leaves, and from every leaf we going through this direction and checking if we can go less. Yes, if we can go less than in this direction, then we simply this out degree decrease by 1. For example, here was 1 because we can go here, and we simply decreased it. So was 1, now is 0, and if it's 0, then we pushing to the end leaves. Yes, and every time when we do this, we increase the height. So for example, this we decrease this, so now this is 0, this is 0, this is 1, so not, And that's all, I think, because from this we can, so we can now have this to 0, because decreasing it from this, we can decrease this also, but by 1, and here was 2. So okay, and so on, so on, so on, to the point where we no leaves. We have the check everything, because yes, because if we don't check it twice, but why we don't check it twice? We check it once because we check only this tab that is in the matrix bigger than our leaves. So if you have here on the leaves, you don't check it because it's bigger. So it's in the end is yeah, there will be an end, and we check these leaves. It is in one function, and this is integrally, not recursively. But the previous one we can also write Italy, but here is more. It's not so simple, this solution. This is not, the previous one was better, but this also works, and also is good. Thank you very much, and see you next time. Bye.